Welcome to DC School of Magic, where learning physics together is magical. We're doing question 24. In question 24, we are in topic forces, density, and pressure. A climber is supported by a rope on a vertical wall as shown in the figure. In the figure, you have a climber indicated by the point mass. You have a wall, and this guy is supported by a rope T at 18 degrees Celsius. The weight of the climber is 520 newtons. The rope of negligible weight is attached to the climber and to a fixed point P. So P is the fixed point where it makes an angle of 18 degrees to the vertical. The reaction force are at right angles to the wall. The climber is in equilibrium. Again, remember the conditions of equilibrium because in the past we thought it was stationary, but not really. It's based on two very important things. There is no resultant force in any direction, no resultant torque at any point. Because of Newton's law, we know resultant force can lead to two conditions. One is stationary and one is constant velocity. Because of the diagram in this question, we know this must be stationary. Okay, so always remember the criteria, the physical criteria used to do your questions, and they'll allow you to understand the question easier. A. On figure 24.2, by drawing a label vector triangle, it represented the forces acting on the climber. So you have a weight. In this case, you have to realize weight is the largest force here, which is then balanced by the tension force and the R. So you just need to draw a labeled vector triangle. So how to draw a labeled vector triangle? Quite easy. You have two other forces, T and R. And these two need to combine to allow you to give you this diagram. So how would you add them together? So if it was me, I'll draw a small graph. I'll just draw T and then R will be like this. And then what you realize is if you actually draw it here, you realize that your weight is actually not the hypotenuse, okay? Not hypotenuse. So we have to draw it in another way in order for this to be bigger. So what other way can we try to draw it? Instead of thinking T, why not we start with W? Let's say W is here. We got R here. R can be here or here. And then we got tension at 18 degrees here. The other picture will be here and as shown in this diagram. So did we get it correct? Did we mention is W truly the hypotenuse? Well, we try again. What other ways can we draw this? Another way to draw this would be just following the diagram. 18 degrees, weight downwards, R in this direction. So let's then say this is the diagram. This is only 1 mark, 2 marks. We already have the important components we need. We got the angle shown, the arrow shown, the labeled direction of all the forces shown. So, let's go to the next question. B. Resolve forces or use a rectangle to calculate the tension in the rope. A1. We need to find tension. So, if we want to find tension, we draw another coordinate, another line here. Alternate angles, here's 80 degrees. We can either choose the horizontal T component or the vertical. Horizontal T component leads to R. We don't know R, we know T, so we're not going to use that. Let's try the vertical. We got T, and we got a value. That means T is the only variable. That means we can use this. So let's take our upwards position to be positive. This is forces. Resultant force equal to ma. Object is equilibrium, so it's equal to 0. We got T cos 18 positive, and weight 520. So T is equal to 520 over cos 18 degrees. I'm not calculating this, so you pause the video and calculate it. When you return back, you should have a value of around 547 newtons. 2. You define the reactive force R, so this one is quite easy. We can decide to be positive. Resultant force is equal to ma, is equal to 0. So we got T sine 18 degrees, T sine 18 in this direction, which is opposite this, so it's negative, plus R. So R, keep here, this one move to the side. R is equal to T, is 547 newtons, sine 18. If you worry about simple figures, you can use the original value, which is just 520 sine 18 degrees over cos 18 degrees, and 520 times tan 18 degrees. So you calculate this, you pause the video, and then once you unpause, you see the value to be around 109 degrees. So, the next part we have to do, the climber moves up the wall, and the angle the rope makes with the vertical increases as you go up the wall. Since you remain stationary at this height, therefore the angle that is created between you and the wire increases by quite a lot. So another expression here. So basically C states that the further up you go, your theta also goes up. Explain why the magnitude of tension in the rope increases. They ask you why would your T also increase. In this case, we just use equations. So let's check which equation we can use that relates to T. You can see this one relates to T. Weight is constant, same person. You just move it upwards. So how do we know whether the angle goes up or not? T is equal to 520 cos, let's say this cos theta. We want theta to increase. What happens when this theta increases? Overall, your cos actually decreases, and therefore overall, on your right increases, on your left increases. Therefore, our explanation is this. For theta is larger, as theta increases, hence cos theta is smaller. So cos theta is smaller here, is smaller. Using T is equal to W cos theta, which is this guy here. Hence T is larger. Back to the question. Just now I said a mistake. I said W should be bigger. Is it truly bigger? Let's check it out over there. No. From our calculation, the physics has told us tension is the biggest at 527 newtons, followed by weight 520 newtons, followed by 160 newtons. So therefore, my first prior assumption that weight is the biggest is absolutely out the window right now, and realize that sometimes it's better not to assume. Let's just draw the diagram and let the physics calculations tell us who is truly the hypotenuse. Okay. I hope you understand this video. If not,